There we go. Good. Okay, so ladies and gentlemen, okay, so this chapter is, compared to the previous several, I think it's a particularly deep one for a couple of reasons. I know when I first read it, it took me some iterations and some of the things to kind of grok the full implications of what was being said, okay? And these are a list of some of the important topics from the chapter, and I'm going to as befits their importance, I'm going to grow them, okay? And highlight some features of these. There were a couple sort of topics that carried through some of the previous chapters were used here, and some that were new. One of them that carried through was referential transparency. Can anyone talk about what referential transparency means? It's a fancy term.
Evaluates the same thing in any context?
Yeah. So you don't have to worry if you have a name used, for example. You know exactly what it means, regardless of where it uses. It means the same thing. It's referentially transparent in the sense that we can immediately consider it's referent. We don't have to worry that it's going to be different in different contexts. That it's highly context dependent. And one of the things that they introduce, and if we go to chapter 4 here, and we look at page 49, they're talking about some limitations of exceptions here. And what they talk about is a situation where if they use a criteria for referential transparency. If we have a value defined in a certain way, defined as equal to some expression, if the situation is referentially transparent, we should be able to substitute the definition of that variable, the thing, the value, not a variable, a value. It's only a variable in kind of a colloquial sense. It's a value called y. It's defined as being this throw new exception. And if it were referentially transparent, if it's defined to be that, any place that y appears, you should be able to just substitute that expression that it's defined to equal, and we should get the same results. And his point is that that's not the case. If we have traditional error handling, we have this try block. Inside the try, it handles exceptions. Things that are throwing exceptions outside the try, that are saying, oh, I'm confused, outside the try, those things aren't handled by the try block. And what he's making the point here, or the two of them are making the point, Paul and Runar are making the point, that maybe this is not, or this is not referentially transparent. Referential transparency means, if, among other things, if we have a nice name used for it defined to be a certain expression, anywhere we see that name, we should be able to substitute that expression and get exactly the same results. In other words, we should be able to refer to it by a name or just substitute the expression in for how that name was defined, and we should get the same results. That's something that's referentially transparent. All we have to consider is how it was defined. We don't have to consider where we are now. It's not context dependent on where we are now. Are we inside a try block or not, as to how that's handled. So the fact, he makes the point that this is not referentially transparent in traditional Java or Scala with exceptions, because we can't just substitute in the definition of y where y appears and get the same results. And that's something that's a challenge about exceptions we're going to be coming back to in just a minute. Broadly speaking, a lot of what this chapter is about is a functional means of handling errors. Why is this important in data science? Does anyone remember back to my first lecture? Why is handling errors in a nice way important for data science?
Data is dirty?
Yes. Data is dirty, and that's perhaps the best way to put it. That's a beautiful expression for it. Data is dirty. So what happens, because data is dirty, what often happens?
You've got projects that take a long time to go through, and you won't find there's an error until the end, and then it cracks your whole program.
Okay, so
Or
that's bad. It dies halfway through because of exception.
or you have to create ridiculous exception handling code
Exactly.
that will make sure it doesn't crash.
Right.
Exactly. Now, Scala approaches this in a couple of ways. One is through what's called type safety.
Right.
And what that means is it's analyzing your program when you first specify the program. When you tell the Scala compiler, hey, this is my program. It actually analyzes, is this actually safe? Could this screw up in a big way? And that's in contrast to languages like Python or JavaScript or R or MATLAB, which are not type safe. In other words, there could be a problem in your program and it's not actually manifested. You don't know about it. You can't be told about it and fix it until you actually run the program. This is a big problem for large programs. Okay, imagine it's running for hours and then something goes bad. Imagine running an AnyLogic simulation for 4 hours and then it dies
Well,
suddenly.
I have an example that I just got contacted about last night with
Yeah.
one of the models that someone's using in Calgary.
Right.
They changed the input file to something that should not have a problem, and now they're getting errors. I know exactly where, I know exactly why. Well, not quite why, but I identified symptoms, and I don't know why. I don't know why changing the input file the way it did. They literally just added a new row of something.
Yeah.
And now it's starting to throw errors. I'm like, oh boy.
Yeah, and so that's interesting. And Scala, even when compared with Java, but most notably when compared with these so-called scripting languages like Python, is going to give you much higher confidence that errors. It's not going to ensure that you have an error-free program, but a vastly larger set of errors will be found. Okay, but beyond that, there can be errors because of problems in the data or issues in the data. So maybe you have a division operator and you have a divide by 0, or you have a log of 0, or something like that.
Did Scala find that?
Well, Scala can't find that at compile time, but what it will do is it can handle it in a principled way without throwing exceptions and using the technique shown in this chapter. Now, R does this to some degree, right? Like in R, what you see a lot of are sometimes NAs. Yeah, nah.
Not numbered.
Well, there can be nans, but there could be NAS. Yeah, NAs, which indicate the absence of a value. Okay, and actually, our code tends to be fairly robust for many functions on handling NAs. It allows you to have missing data points. Now, you have to be careful with some things about whether it handles it, and that's just the point. That's part of this whole type safety thing. What we're talking about in this chapter is a way of handling errors that is simultaneously able to tolerate errors, so they don't just crash our analysis pipeline. They don't crash us, midway through a computation, but at the same time is rigorous in getting us to respond to how to handle them, and doesn't require a lot of cruft, doesn't require all this ridiculous code around to sort of reason about special cases and restart the computation.
Another reason for that is because of lazy computation. Lazy computation would theoretically defer errors.
Lazy computation can defer errors.
Which is not necessarily a good thing, is what I'm saying.
No, that's true. That's true. Yeah. Often you want to know about errors as soon as possible. Yeah. Okay, so we're going to talk about problems with exceptions, and then there's this counterposed sort of concept of handling things with sentinel values. What do we mean by sentinel value? It's not so much that. When in traditional situations, we often signal an error. How do we do it? So suppose we return
a number that doesn't make sense.
A number that doesn't make sense. So we return, -1 for something that we know has to be 0 or 1, an index, right? Find this string and this other string. At what index does this substring occur? And guess what it returns if it can't find anything? -1. Or we return a special value That's impossible. So we take the square root and we return a negative value, minus 1.0. So we have a special distinguished value, a distinguished return code. Now, this is an old tradition. This is a long tradition. I refuse to call it a distinguished tradition. And the most famous and the most perhaps rightly maligned of these distinguished values, ladies and gentlemen, is what? We use it for references. If we don't have a reference, we can't find a reference, what do we return?
Null pointer.
Null. And the person who invented null, there was a person who invented null, okay? And that person declared it was $1 billion mistake, which, again, I tend to disagree on. I think it was a multi-billion-dollar mistake. But nulls sort of stand in for something that's a missing reference. It's not there. And the reason it's so bad, one of the reasons it's so bad is what?
You never know the problem until it comes up.
Yeah, it's basically a runtime issue, and there's no forcing you to handle it. And often you throw in a null, this thing gets a null from this other piece of code it calls, and then it can't handle it, and it dies a horrible death.
Oh yeah.
It dies a horrible death. And then some nulls are occasionally just null event loop.
Oh God, don't get started.
Sometimes they're a handle, but they're just annoyances.
I hate that.
Yeah, you should speak with Winchell about it. He's also
goodness.
lacks full fondness for it, as do I. Especially when it's in the middle of discussion with non-technical clients. Just
God.
ignore that. Just ignore it.
Yes.
Yeah. Okay. So what we're talking about here is something that will go beyond the problems of exceptions, go beyond the problems of sentinel values, these kind of stand-in values that are unenforced, that the compiler doesn't know about, care about, and that often end up biting us because we don't handle them. And we're talking about a safe method based on something called option, which basically is kind of a maybe value. Chris Duchin talks about it as a maybe. If this is maybe an int, or I know I don't have an int, okay? So this function returns a maybe double. Maybe it's square root. It takes a double in, and it returns a maybe double. Because if what's passed in is negative, it returns an empty thing. It's not any double. It's an empty thing. But the point is, we know that we may not get back a valid double, and it can force us to handle it. Okay, but it's because it's a value, we can still do maps with it, and filters with it, and flat maps with it, and we reduces with it, and still get out meaningful, robust results without it breaking our code halfway through or forcing for us to have huge amounts of cruft along the way to handle. We can write a nice pipeline, and we know that the pipeline will be short-circuited in a well-defined way if there's an error encountered. Okay, so let's talk about, yes, Kurt.
So as I was reading the chapter, I was trying to think like what tangibly was the difference, because the difference between using nulls and using options.
Mm-hmm.
Because
Good.
with the options, you've got this so the option has a sum or a nothing, sum bracket,
Yeah.
and then a nothing.
Yeah.
So the sum is the value and the nothing is the null.
Yeah.
But I'm wondering if the difference is because you can easily transfer an arbitrary function that gives a single value to one that has an option.
That's part of it.
Difference?
That's part of
You
it.
can do
Also,
the
you can
thing or
perform
whatever.
operations on empty things that are nothing, and they'll return nothing.
For example, I could write a machine learning algorithm that takes in a data set that has both labeled and unlabeled data. And if I can look that if it has a label, it has some of a string or whatever, it actually uses it to create the data set. And then it looks at the nuns and labels them. That would be just
That's
one
right.
way to do it.
That's right.
And
You
I
can
don't actually calculate two passes to the data set if I wanted to.
right. and so this is very closely related, I think, what you're getting at there to what I'm saying. You can write long pipelines. Ladies and gentlemen, much of what we're going to be seeing with Spark and analysis is about pipelines. You do this, that, you get this data from this data source, it's combined with this other data, it is processed through this, you find the values in this range, you extract them, you reduce them in this way, or you divide, you group them by this way, you reduce, you compute this, and you tabulate in this way, da-da-da. It's about a series of steps. Kurt, if you get out along that way, if you get out a value, let's suppose from a filter, I do a filter and I try to find all values greater than 0 from this stream. I will get out an option of double, okay? Or excuse me, it's actually a possibly empty stream, which you can think of as equivalent. Or and out of reduce, I may get an option of double. And there, I can still perform the successive operations on it. I get out that thing partway through, maybe that's nothing. But I could still call filter on it, I can call map on it, and so on, in a meaningful way, all along the way. It doesn't break the pipeline halfway through just because I happen to not get a value at this point. With nulls, generally I can't call things on them. I can't say, well, filter this, map this, group this. Whereas with missing values, with option, I can. That's one thing. The second thing is if I have code that's processing the result, it won't let me get away with just treating it as any old double. Because it knows, wait a minute, this may not be a double. You have a maybe double. You may have a double or you may have nothing. You have to handle both cases of this in your appropriate handling of it. So it's not going to let me just be sloppy and say, oh, this person is a mother, I'm going to find her name. Because if it's a null, there's no enforcing of the compiler, you got to handle this case or it could be null. Whereas with an option, it handles it.
Basically something like option none, especially none, is basically a compile time version of null that allows you to handle all that stuff.
So yeah, it's a compile time type, what we call type safe.
Right. It's
watching out for us. Here's looking at you. It's looking at your code, okay? So, ladies and gentlemen, let's go to our Scala shell, shall we not? Let's import Scala util underbar, okay? And I will try, and I did post yesterday in a belated fashion my code from the last time, and I have to praise the students, and they sit around this table, who have urged me to post my come on in, Aiden. Come on in. Hi.
Maybe later. I will watch your videos because you were in the meeting.
Oh yeah, we talked to Doroshenko.
Yeah.
We have just started if you
Okay.
want to check.
You have your laptop. I
Okay.
will give you my laptop.
We're just starting the Scala shell now.
We're just starting the Scala shell.
Okay.
They heard
Need a
me.
chair.
They heard me engage in monologues and
That chair's kind of broken.
and diatribe to some degrees. Not quite Jeremiah's, but I was making utterances, and now we're going to do things that are interactive. Okay. Okay. I did talk about projects, and you want to review that video because that enjoyed some student input as well. Okay. So import scala.util.underbar. Okay. Okay. Okay, now what we're going to do is we are going to say that we can take sum of 3, for example. This is an option containing the value 3, right? Which allows us to sort of represent, okay, we may have a 3 or something else. And in general, we could say, value v is an option of int, right? Here. Oops, what am I doing? There. And it can equal 3, in which case it will be unhappy. We'd have to say sum of 3, okay, to indicate that it holds that. And how do I tell it that it holds nothing? It holds something that's empty. None. Right? Yeah. Option of int, it holds none, ladies and gentlemen. Nothing is a distinguished thing that's used as a sort of a type, so it's none that we want here, okay? So let's I stand remiss. Let's call one v2 and call one v1. This one here. Okay? Now you'll notice here that we, by virtue of it being an option, we have certain things we can do with this value. One thing is, and here's a set of things, right? I could ask, is empty, for example? Now, I want to highlight something. You see all these things I did. I just did autocomplete, right? And we have a certain number of things we can perform with this, as you could see. Kurt, I would draw attention to the fact that all of these things could be performed even if it's null, if it's none. All these things can still be called. They'll just behave in a reasonable way given that it's none, okay? So, no, they actually won't throw an exception. They will return back a value which is typically none itself because we've applied it to that. We'll come to that. We're passing it along, which allows the rest of the pipeline to complete. But it's actually short-circuited in the sense that you're not actually doing a lot of work. You're just passing it along.
Whereas if we were just using null, as soon as we asked, hey, null, can you give me a stream of, and the system will like,
yeah, that's exactly right. And that's how I that's a similar audio sort of utterances that I imagine as well.
One question I have is that can we literally handle none? Like, if I get none,
yes,
call this entire algorithm that tries to fill in value for it.
Yeah, and it's this thing, it's a great thing. Is empty. So we can ask, is it empty, for example? Okay. And that, so V1, you may remember V1 is sum of 3. V2 is none. And we can ask in both cases, is it empty? Okay. That allows us to ask, is this something that needs something that is missing a value?
We can also use sum and none in cases.
Yes.
Okay.
Yes.
That was what I was trying to
Yes, we could do it in a case context, and we could look at how you do that. But beyond that, so again, these represent kind of maybe ints. We might have an int or we might not, right? We might have an int here or we might have no int. That's what these represent. Okay, let's do some more though. We could say v1 get or else. Okay, ladies and gentlemen, maybe if it's not a well-defined value, we want to treat it as 0. Okay. And here's v2. So here we said get or else and it returns 0. Why is that?
It's saying get the value if there is some value there, otherwise.
Yes, exactly.
Oh, so that's a very easy substitution.
Exactly.
Function.
It's saying sort of, hey, handle it with this value if I don't have a value right now.
If it's
right? So then I don't have to explicitly test, is it empty? I just say do get or else this thing, okay? Handle this as this thing or else. Now, you'll notice that there's, these are amongst the things, is empty here, for example.
I can call an iterator on an option, that's fine.
Yes. That's fine. And we could map it, right? So we could say, for example, v1 dot map, right? Now watch this. Let's do something which squares it. How are we going to do that, ladies and gentlemen? How are we going to do that? Well, we could do
arrow x.
Yeah. Here we go. Here we map it. Okay. So we get back 9, right? Right? How about this? What do you think will happen if we do this?
No.
We'll get back none. Now, if that were null, what would happen? It would freak out. Yeah, it would exhibit displeasure of the computational kind. And so this is significant. Could we filter it? Let's go.
The answer is yes.
Indeed.
Wait, but more importantly, the implicit type of the function you gave it was option. It wasn't int. So therefore, if I wrote a function
no.
that would not take in an option, I couldn't use it on option.
Well, okay. So
That's-
no. So this is this is going to get to one of the more profound implications of the chapter. Okay, and I think we're going to need to spend next time on this chapter as well, because it's no. This is, Scott. What you've put your finger on is one of the most significant things. Ladies and gentlemen, this function that I am mapping on V1, what is the type of int? Well, I could test my intuition here. I'm going to say I'm going to do something that's this. What's going to happen if I say that? It's going to be very unhappy because option of int doesn't actually have a value. What type is this? What type of function is this?
It's a monad.
Okay, it is a monad. V1 is a monad. Here, ladies and gentlemen, it's taking a function. Okay, this is going to take some time. And if there are epiphanies that cause people to cry out in delight, I will not object, because it perhaps is worthy of that. It's just it's a great thing. Okay, I'm gonna have to communicate this greatness to you if I can.
I think you're doing a good job so far.
Okay. Okay, ladies and gentlemen, this function is a function of ints, even though this thing to which we apply it is not itself an int. What is V1? What is the type of V1?
Option.
It's an option of int, but we are mapping it
Over.
we're mapping a function over.
it.
That's exactly
We
right.
don't care about the function.
That's right. So here, yeah, we're not particular about this function, although soon we'll get to a function that's about which we should be particular, okay? Okay, ladies and gentlemen, we are mapping a function over this. It's almost as if you could think about V1 as a collection with 1 or 0 elements in it. Either as 0, in which case it's null, or it's 1 where it is the value. I prefer to talk about it as a container. And the technical term we're going to use for it is monad. You heard it from Scott's mouth earlier. And he's exactly right. This is a monad. And it's a container. It's kind of a wrapper for this thing, okay? There's bigger wrappers. There's streams. And there's arrays, etc. There's that type of wrapper. And the point is that this function is being applied to each element, which is only 1 or 0, of this one, okay? So here we are mapping this particular value within it using this, and guess what we get back? What do we get back out of this? The result of mapping it is what? Well, it's a container 2. It's the thing over which we mapped it, the option was a container, containing 3, and we're performing this map over that container. We get back a container that has the square of each element in the original container, which is just 1 and 0. But if we apply it, ladies and gentlemen, if we apply this to V2, what happens? What do we get back?
None.
We're going to get back none, because it's as if it had 0 elements in it, right? It has nothing to apply. We're getting back a none. It's not anything. Okay.
So it's like, so pardon me for
Yes.
things. So basically, using option is like having a for loop over a collection that has only 1 or 0 members. If there's 0 members, it executes the loop, but it never actually does anything.
You can think of it roughly as similar to that in a certain sense.
But now it knows it has nothing, and therefore
Correct.
can do it.
That's right. And so if you then apply filter or a flat, let's do a filter here, right? V1 dot filter, and we say, is this thing greater than 0? What will we get back? What do you think we'll get back?
On V1, you should get true. Is it an option true? Option boolean?
Yeah.
Oh, no, I'm sorry. You're not getting the condition back. You're going to get
Yeah.
the value back.
Yeah, it's the value back. We're getting the subset of the values for which let's do this. What do you think we'll get back now?
None.
Oh, wow.
Instead of false.
Yeah. Okay, now
So wait, whoa. So if we throw in a collection of options,
yes.
we retain the entire structure of the data moving forward.
Yeah.
As opposed if we had 10
That's
ints,
right.
1 through 10, and we asked filtered on
Yeah,
something everything greater than 4, it would return to me a collection of 5, 6, 7, 8, 9, 10.
that's correct.
Whereas if I give it an option, like a container of options from 1 to 10,
Yeah.
it would return none, 5, 6, option 5, option 6, or some 5, some 6, etc. Right?
So we would need to apply it then a function that mapped from option to option.
Okay.
But we could do that, and yes, we could do that. That's correct. So
Interesting.
we could get these kind of placeholders where the ones that were filtered out were
Well, it might be
located.
important
But yes,
for
we
data
could do it.
sets.
We could do it. It wouldn't be a simple matter of just filtering. Okay, how if we do V2 filter this? What are we going to get?
None.
Yeah, and secretly, it doesn't actually have to do the work of doing this. This gets to what Scott was saying. It's not actually going through on each element of it, because there ain't no elements to do it on. So it's just going to be returning 0.
Question.
Yeah.
Is it evaluating the expression?
Okay, that's a good question. No, it's not evaluating the
Okay,
expression.
so as soon as it says
It's
I'm
short-circuited.
calling filter on none, return none. I don't
That's
even
right.
look at what the function is.
Exactly.
Ooh.
Exactly, ladies and gentlemen. And that is a monadic concept that in certain cases it doesn't have to do the work to apply it. It's just going to say, look, nones, if we apply a map to a none, it's a none. If we apply a filter to a none, it's a none. If we apply, okay, let's try something else, ladies and gentlemen.
Can I have a
Indeed.
So if you take V2 or V1 plus V1, it's going to give you an error.
Okay, so
Because
if
V1's sum 3.
right, suppose we were to, okay, I love this Krugerian idea.
So if you go
This is
V1
great.
plus V1, what
Yeah.
do you get? I think you get an
So
error.
what would you get? What do you think you'd get, ladies and gentlemen?
None? No.
Because V1 is sum 3. It's 3, right?
I don't know.
But if you take
I don't know how to do a plus. Yes.
if you say V3, if you create a new variable called
Yeah.
V3 and you just set it equal to 3, not option 3, just 3,
Yes.
right?
Yeah.
Then you can do that, no problem. But
Yeah.
then you can't do .filter because filter operates on containers,
Okay.
right? Is that right?
Wait.
Filter operates
Filter
on,
8 operates on containers. Map operates on containers.
on containers. So basically you can options what you said was a monad. A monad is a container of 1 or 0 things.
Yes.
So anything that you can run on containers, you can't treat option ints as ints because if you go option
Except
int
we
plus
are when
option
we apply
int,
functions to it.
Okay, so watch
but you
this.
can't do that to singular ints. You can do it to containers of ints, no problem. If you
So-
make a container of 2 ints, you could do a map or a filter on it, no problem. But you can't do it a filter on a single int.
Okay, but watch this. So I'm thinking about the best way to respond because you too, like Scott, have put your finger on a point of greatness. You've sort of highlighted a thing that has deep implications. Okay, and I don't want to treat this lightly. You're right that you cannot perform this because we are adding together two ints directly, right? And what if I tried to do? Suppose I wanted to do what's that?
Val V3 option int
Okay.
equals V1.
Okay, so suppose I want to say val v3. We could try this. It turns out it's not going to work, but it's a good idea. Let's go see what's going on. V1 plus v2. Alas, it's trying to even turn them into strings because that's all it knows to do. It's just I can't find a plus. Maybe if I turn them into a string, then I can do a plus. And it's thwarted, ladies and gentlemen. It's thwarted in this beautiful idea. Okay, what we'd like to do is lift plus. There's a notion of lift, ladies and gentlemen. Lifting here bring a function from A to B into option A to option B. So it operates on options. We'd like plus to be able to operate on options transparently without creating our own option plus operator that we have to explicitly define. If only it could do it. Well, ladies and gentlemen, the truth is it can. This is the beauty. Now we could try again. We could kind of try to flap around some more, right? Let's try to flap around, right? We could try to say v1.map. How if we said this? X plus v2. What is that going to do it? What would happen there?
X plus v2 still doesn't make any sense.
It says it cannot be applied to an option int. Oh. Now we could do this dot get, but bad things might happen if it's a null.
So get
It's
or
a
else.
none, right? We could do get or else, and it says int is okay. Okay.
That's even worse.
Um,
Now it's treating it as an
So actually, sorry, I'm.
You want no brackets.
Yeah, get. Okay. Yeah. Thank you. It says okay. I can't do it. It's a bad value.
That's basically no pointers.
Yeah, exactly. Okay, ladies and gentlemen, what if, though, we were to do something like this? What if we were to do this? Think about this, what I'm about to do, because I would warn you if this were drawn from King Lear. King Lear, they said, this way lies madness. But in fact, ladies and gentlemen, this way
Can we
lies
map it to
greatness
itself?
here, okay? What's that?
Can we map it to itself?
Okay, so ladies and gentlemen, flat map. Flat
Yes.
map is going to allow us to give it something that could return itself an option of int. With map, we had to give it something which returned an int, right? Here, so it takes an int and returned an int. With flat map, we can give it something that returns an option of int. The same as the type of thing we're applying to which we apply it. Oh, ladies and gentlemen. So here we can do a flat map and then watch this. Ladies and gentlemen, watch this. Okay, we could do x.map. Okay, and we could basically do whatever value we have plus, okay, and actually, sorry, y.map. Whatever value we get.
Can you pull the screen up a bit? It's a little hard to read at the.
Oh, is it going off the bottom here? Okay. Okay, there we go, ladies and gentlemen.
Yeah.
Okay. Sorry. X plus v. Okay. X plus v. Okay. Sorry. Okay. What am I saying? Y. Sorry. I'm screwing up here. Okay. Okay. So we want. Okay. This. So this. No. We want v2. Okay. V2 dot map. Yes. Exactly. Okay. There we go, ladies and gentlemen. There we go. Okay. So what hath we done? What hath we wrought here? Okay, let's create a V3. I like this V3, and this is going to be a sum of 3 here. Oh, sorry, of 4. Okay, just give it a different value. Okay, and here we're going to do it like this. Okay. So here, V1 and V3 added together will be V7. But if we want to add together V2 and V3, what do we get? We get a none. Okay, what have we done? Okay, ladies and gentlemen, here we've done a flat map. So what this is getting, what does flat map take? It takes something which takes in an integer, the thing that's contained in V2, and it returns a what? An option of int. This, ladies and gentlemen, I would argue returns an option of int. And you can verify that because v3.map of, v3.map of of whatever I give it. Oh, come on. v3.map of this gives back a sum, and it gives back an option event, okay? So this thing here returns an option, I would argue. v3.map of anything meaningful gives back an option event, okay? Now, this option can use, here we're going to compute what this option is. So we do v3.map, and what is the thing that we're giving it? Remember, when we're taking a map of an option, what does it take? What's the type of thing? When you take a map of an option, we did it earlier.
It takes whatever the data type inside the option is.
Yeah, it operates on ints and returns ints, right? And for this option event, right? Ladies and gentlemen, is that right? Okay, so let us do the following. Let's reason that through. So this is something that takes in an int and returns a what? Well, an int. I told you, map, when applied to an option, we saw it earlier, it takes a function that takes an int and returns an int, right? That's what map does when applied to an option event, okay? When applied to an option event. We're just dealing with that. So, ladies and gentlemen, let's think about what's going on here. So, this function is one that takes an int and returns an int, okay? It is applied to v3. Let's reason about the cases here. Suppose v2 is none. What's this going to return?
None.
None, because it doesn't even have to perform this flat map. Flat map takes in an int. There ain't any int to perform on. So this is going to return none.
Right.
What if v3 here is none?
Then you're mapping v2 to none.
You're performing this map on, if v3 is none and v2 is not none, x will have some int value, but this will be short-circuited because v3 is none. And it won't even need to perform the map, right? It doesn't need to perform the map because v3 is none. So it'll just bomb out with none, right? v3.map would return what? If v3 is none, what will v3.map return?
None.
None. Okay, now let's take the case where v2 is some value, like 3. v3 is some value, like 4. What is this going to do?
It's going to map v3.
Okay, yeah, okay. So let's consider this innermost, and we'll work out for there. What is this? Here we have v3, and it's performing this. Well, actually, let's think about it from the start. Sorry. So this v2, or whatever this is, if v2 had some value, and we do a flat map over it, what is x going to be bound to?
v2, maybe the value.
Whatever value is in v2, right?
Right.
If v2 is none, this flat map won't even be applied. It will return none. If v2 has some value, x will be that value. It's some value, it will have that value, right?
Mm-hmm.
This x is an integer. So if v2 is sum of 7, x would be what? 7. It would be an integer. Okay.
Huh.
Now, v3, if v3 is some value, say 4, and we map this function, what will v be? 4.
Right.
And then we will add together what? 7 and 4.
And then we just
And that's going to return
11.
Sum of 11.
Sum of-
Because remember, when we did earlier a map on an option, we got back what?
The option.
An option, ladies and gentlemen.
Okay.
It performs the map on what's inside of it,
But it returns
right?
the container.
And returns the container of that thing.
So this is a completely type-safe way of adding null values. Because,
Yes.
because
Yes.
If
Yes.
you have an option that's none, you don't perform the function that would throw the error if you just didn't wrap it
That
in
is
a container.
that is correct. But I'd like to show you something
That's
of
amazing.
even greater beauty. Okay, now I could change this. Obviously, in general, we're not going to do it on just these couple values, but I could have x1 gets v1, x2 gets v3, and yield x1 plus x2. Let me try this. I don't think you're going to be able to do it this way, if only you could, but it would be great if you could. No, it's not going to be able to do it. You actually have to have this little syntax here. So this gets basically the value in there, this gets the value in there, and then we add them together. Now, we can do this with more than that. So we could do, for example, we could have a long series of computations here involving this. Here we have x1 and v3, and we could do z equals x1 plus x2, and we could have a gets z squared, and we can do yield of A. Oops. Oh, sorry. Sorry. What did I?
Bracket?
Sorry. No. Sorry. Okay. So what did I do? Oh, I see. Okay. Yeah. No, we should have been able to add those. So flat. Oh, I see. Okay. Yeah. Fine. Yeah. Sorry, I shouldn't have used this syntax for that. I think what we should have done is something like this, and I think it might be a lot. Oh, a thing of beauty got destroyed by an ugly syntax. Okay. Here we are. Copy, paste, boom. Okay, and we'll do those things again. Sorry, it's a bit painful on this. Yeah, when you have the left, you'll notice that what it said there was actually a hint as to what's going on beneath the covers. I'll just retype it. Okay, and then we could do here, and we should be able to do some computations. I'm actually not sure here of the syntax. I think we might be able to do x1 plus x2. Is that correct?
V2 or V3?
Sorry?
V2 or V3, because V2 is already known.
Oh, yeah. Thank you.
We'll see if it throws an error.
I think it's going to be unhappy with this, but yields y. Okay, I'm going to have to figure this out. So it does work, yeah.
Well, that's because it's a none. What happens if-
Exactly, but if I had done, yes, so Anahita was correct. I could have, if I wanted to demonstrate it with actual values, I could have done v1, and x2 gets v3, right? And done this to sort of, here's a nice little variable that computes the sum of those two, and then I'm going to have y just be z times z, that value times that value, and yield y. There we are, ladies and gentlemen. So what is v1? One of them was 4, one of them was 3. We added them together, got 7. We squared them, and yielded that. In short, ladies and gentlemen, we are performing computations here
So
on the
for
underlying values
loop,
when they're available.
flat map and map are happening.
Yes.
For loop.
Yes. this is performing for us behind the scenes automagically the flat map and map. That's what's going on
How
here.
do we know that?
Because there's an error that tells you.
Well, I saw the error was that there's a flat mapping, but
Yeah,
the issue
right here.
is that, I mean, is that because you're doing a for? Is that because of the?
That is what the for comprehension means. It's defined in terms of flat map and map, and it's designed to allow you to handle monadic values, just specifying the operations on the values to be, if there's a value there,
Mhm.
specifying how to perform it on that value, and then returning it. But if there's no value there, it will return none. Ladies and gentlemen, this is a trivial little thing, but you could imagine applying this for loop to, you could imagine applying it to whole, I mean, this here is an option, this is an option. And it's kind of a nice way to perform math on those option values in a type-safe way. In a way that's robust to errors, allows us to write out the full computation in a very clear, successive way, but it still safely handles nuns. At any point, if one of these conks out because it's a none, the rest will be short-circuited. It won't actually perform it. If there's an actual value in these things, it will perform it. But, ladies and gentlemen, the real power of this starts to happen if V1 and V3 are streams or collections, and this is being performed on each element of that collection. Okay? And you can imagine some of these things, moreover, as yielding values that could themselves be none along the way. Like 1 is A divided by B, yielding none. Okay? So we're going to come back to this. We've just started to talk about it. But this for comprehension unpacks to a for all here and a map here, where inside the map, this math is being performed. And then it's yielding up the value. So what we see is sort of a type-safe pipeline here of successive computations being performed safely, even in the presence of possibly missing values. And the whole point is the missing values are occurring here in a container that we call option, but in general they could be occurring in other containers, streams, arrays, sequences, vectors, all these different types of things. That's where these could be occurring, okay? So we're going to come back to this next time, ladies and gentlemen. We're going to come back to this issue of option and explore this more and talk about a couple of additional features here. Problem with exceptions, problems with sentinel values, talk more about option, the option value. By the way, I showed you get or else, but there's also an or else where you can tell it do this, evaluate this extra thing, like go get the value from look it up in a database or whatever, if the value is missing. And we'll see if we can come to understand it, and then we'll talk about either and try as well. This book doesn't really talk about try, but try is an incredibly powerful feature of Scala as far as I'm concerned, and it interoperates. Look at this. Val, v, you know.
Wait. So it's setting the value of that variable to a failure.
Yeah, so A1 holds a value,
And that value is an exception.
or it could hold, A2 is 3 divided by 2.
No.
It holds this. So A1 and A2, and I can say A1 dot 2 option, and I get back a none. I could do A2 dot 2 option, I get back a sum of 1.
Someone.
Ladies and gentlemen, try allows you to evaluate an exception, and it will keep track of what the exception is in this.
So you can track it.
Yes.
But this is what we are trying to not have in our Scala programs. I mean, we want to manage the exceptions, but we don't want to our programs to lack the purity and the. I mean,
This is true, but there are times where
we want to
what
have
we
the
want to
exceptions.
do is we want to be able to write programs that are operating as if they're operating on the normal values, but if they exhibit errors. We don't want to write lots of cruft around this. If this thing is null and that thing is null, then we do this. And I've lots and lots of sort of special cases. We want to be able to write a clear program whose flow is clear in terms, and there could have been 10 of these here, right? 20 of these. It could be a whole pipeline of processing. We'd like to be able to write with that clarity about what's going on. But if there is an error along the way, we often will, first of all, we want this to just sort of appropriately bomb out, but we want to have information about it. We don't want it to throw the user an error, but we want to know what went wrong along the way. And that's what try allows us to do, because it allows us to capture the occurrence and knowledge of an error as a value. Along the way. So we could be performing a try to read this data from a database, or to read it over the web, or to get it from user input. And guess what? Sometimes users make mistakes in entering things, or over the web the connection is down, or there's a problem with the database right now, or it's a missing value. And try allows us to try these things, and if they fail, it's still a value, and you can still operate on that value. You can still operate, and guess what, ladies and gentlemen? Guess what the great thing is? You could write this. I showed you how you could convert it to an option just for conceptual clarity, but guess what? You could write this with respect to your try values.
It's just a container within a container, though.
It's actually
try.
just a container here. Try is a container.
Oh,
Try is
it's not containing within it an option?
No,
Okay.
no, unless we could convert it to an option, but by itself, it's just this. So it's just another monad. So we could put it in here, the two try values, and add them together. If they're real values, we just use them. Otherwise, they are.
So how does it fall through? If for example, let's
If
say
it's an error, it just will short circuit this whole thing and get out an error.
right, but it will still tell me that it's a divide by zero error.
Correct.
Okay.
Let's do it. And we're over time now. And
Sorry.
and others are.
Well, but could I also find out when it happened in the process?
That's a good question. And I'd have to think about that. Okay. Here's X. There we go. And A2 and then we could do Z is x1 plus x2, and I will yield Z. Right.
Nice.
It tracks it through. Right. I could alternatively have done, this thing along the way. This is an area where the Scala shell is not at its greatest, but
We don't use the sublime, correct?
sorry.
Sublime Scala rep.
Yeah, we could. That's maybe a better one to use. I'd be interested in talking with you about that. You're using it?
Yeah.
Wow, I'd like to talk with you about that. You prefer it?
Yeah.
Okay.
For all people.
Okay. Ladies and gentlemen, yield A, right? Here we get out that because we had one of these was a try, right? Was a failed try. If these had both been legitimate tries, we would have gotten a real value out.
Can we
Can
translate the string into this?
Can we sum up, for example, two tries? Like try
Yeah.
this plus try that?
Yeah, legitimate tries,
Yeah.
like ones that yielded real values.
Yeah.
Oh yeah,
Like
yeah.
try V1 plus try V2.
Sure.
Well, here,
That's kind of what's going on here.
What I'm trying to figure
It's-
out is
yeah.
can I feed into these different monads? Could I feed into this for construction?
Yes, you could.
Option and a try.
Yes, you could. Yeah.
Oh, geez, I have to know how that works. Anyway, sorry.
Yeah. You could do that. So
You have to do it now.
so here I'm just going to add it to itself, right? X1 plus X2, A equals Z times Z.
If it's like a rate function or something like that.
Yeah.
then will it work? like for the things with pipeline?
Well, you could give it it needs a function. Could it be a curried? It needs to get back. Yeah, but you get back an option of a function then. But you could give it a curried function, one that already part of it has been evaluated. Now it's just a function which maps ints to ints or something like that. You could certainly do that. Okay? But I need to meet with Hal, and then I need to meet with another student. So we'll come back to this on Tuesday. Good or not? Okay. Ladies and gentlemen, we're touching beauty here, and I'll try to iterate again on this before we go on to chapter 5, which is also quite challenging. Okay.